In this problem, we're going to again look at projectile motion, but we're going to have this added complication of a wind gust. So for this example, we have a baseball, which is hit when it's 3 feet above ground. It leaves the bat with an initial speed of 152 feet per second, and it also makes a launch angle of 20 degrees with the horizontal. So that's my angle of elevation from the bat. At the instant the ball is hit, there's an instantaneous gust of wind which blows in the horizontal direction, directly opposite to the direction the ball is taking toward the outfield. That's going to add a horizontal component vector of negative 8.8 I feet per second. All right, and that's going to be added to the ball's initial velocity. I went in there and I made it look bold. Now it just looks messy, but this I is indicating that I vector. All right, so that's a vector. For part A of this problem, we're going to find a vector equation, or rather a position vector, for the path of the baseball. So I'm going to start with my initial velocity equation. So my vector V naught, I've got V naught, the speed, cosine alpha I, plus V naught sine alpha J. And then because this wind is blowing in the exact opposite direction, I'm going to say minus 8.8 I. Now, we know the initial speed, 152, as well as we know the launch angle, 20 degrees. So my V naught vector is 152 cosine 20. And we have minus this I vector, so I'm going to come over here and say minus 8.8 I. And then I would have 152 sine 20 J. So this gives me my initial velocity vector. And we know the position of the ball when it is hit. So we have an initial position. So R naught, we haven't moved 0 in the horizontal, but because we are 3 units above the horizon, my R naught is just going to be 3 times my J vector. Now, if we recall from our previous video, we noted that acceleration, which was the second derivative of position, is negative G J. And if we integrate that twice and we use some initial conditions, through some magic, we can say, well, clearly R equals negative 1/2 gt squared times my J vector plus V naught times T plus R naught. So subbing what I have calculated for V naught as well as R naught in here, I'm going to end up with my position vector at any time t, r of t is negative 1/2. Since we are dealing with imperial units and we're talking about feet, we use 32 t squared j. V naught, so I've got plus 152 cosine 20 minus 8.8 I plus 152 sine 20 J. And so all of this is times a T. And then we also have my R naught vector, which is just going to be plus 3J. So with a little bit of careful manipulation, our position vector is, I will start with my I piece first. And notice that t is going to distribute here. So I have 152 cosine 20 minus 8.8 t. I have that many t times my I vector plus my j vector. I have 3, and then I have plus 152 sine of 20. That piece right there needs to be multiplied by t. And then the negative 1/2 and 32, I have minus 16t squared. I have that many j. So pause, make sure you understand where I got all of those different pieces from. This t right there that distributes, I could see that getting lost rather easily. What we have here though, this represents our position function. So now let's do part B and C. So I've brought my position vector in, and we want to know how high does the baseball go and when does it reach a maximum height? One thing we know is this maximum height, this will be reached when the vertical component of our velocity vector, right? When the velocity is 0, that's when we're going to reach our maximum height. Well, I have my position vector here, and this is my vertical component of the position vector. So we'll say that y equals 3 plus 152 sine of 20, that's my coefficient on t, minus 16 t squared. So the derivative of position is velocity, dy dt, or rather derivative of 3 is 0. I have this coefficient left, the t goes away, and then the derivative of negative 16 t squared is 32t. So we want to solve this part equal to 0. And this should be pretty easy. I'll subtract that term over and divide, and I've got t equals 152 sine 20 divided by 32, or rather at approximately 1.62 seconds. So that is the time at which the baseball has reached its maximum height. That is when it's reached the maximum height. And if we want to know how high we will go, we just need to plug this time back into our vertical component. We don't need the entire position. We just want to know the height. So that's why we're using the vertical component here. So this would be y equals 3 plus 152 sine 20. My t value, I'm going to use my approximate on the paper, but you should use exact values in your calculation. So times 162 minus 16 times 1.62 squared. And calculating that, I get that my height is 45.2 feet approximately. So it reaches a maximum height of 45.2 feet at approximately 1.62 seconds after the impact with the baseball bat. We have 1/3 part here. And now for a third part. Assuming the ball is not caught, find its range and flight time. So what that means is when does the ball land? At what time does the ball hit the ground? And how far has it traveled horizontally? So in order to find that time, we are going to set the vertical component, our position function, equal to 0. So that vertical component, we've got negative 16t squared plus 152 sine of 20t plus 3 equal to 0. So this quadratic, linear, constant. This is a quadratic equation. Ideally, we want to factor it, but we know that most equations aren't factorable. So we'll use the quadratic formula. Negative b plus or minus square root b squared minus 4ac, all divided by 2a. So that gives me negative 152 sine 20 plus or minus the square root 152 sine 20 squared minus 4 times negative 16 times 3, all divided by 2 times negative 16. And with some super easy algebra, you guys can calculate this and you will clearly get t is 3.3 or negative 0.06. Obviously, we can't have negative time. So what we say is at t equals 3.3 seconds, the ball lands on the ground. How far does the ball travel? Well, the horizontal distance is the x component at t equals 3.3. So my x component, or my range, r, is going to be 152 cosine 20 minus 8.8 t. So we want to find the range when t is equal to 3.3. So at this point, we just plug that in, and I have 152 cosine 20 minus 8.8, all of which is times 3.3. I end up with approximately 442 feet. So that is how far downrange this ball is from its initial position when it was hit. All right? So if you have any questions, feel free to email me. That concludes the lecture for vector valued functions regarding the integrals of them and projectile motion.